Hey everyone, welcome back to Get Your Tech On, episode 102, the show where we dive into all things DOCSIS and cable tech. I'm Brady Volpe, founder of the Volpe firm and chief product officer of OpenVault. Today we've got a fun and insightful episode for you as we explore the SCTE TechExpo paper titled HFC, the gift that keeps on giving. And let's be honest, HFC just keeps on surprising us. We're going to talk about tap values, fiber segmentation, amplifier setups like Node Plus 6 and Node Plus 0, and some DOCSIS 4.0 tech highlights. Oh, and yes, we'll answer the age-old question, can our trusty F connectors handle the new DOCSIS frequencies that we're seeing in DOCSIS 4.0? Stick around, it's going to be full of surprises. And now, joining me as always, the myth, the man, the DOCSIS guru himself, John Downey.
Oh, it's great to be back, of course. I know there's a joke in there somewhere about HFC, the gift that keeps on giving. There's a joke in there somewhere.
It's between your teeth joke. So it's actually, I know, John, we'll see the back of your head shortly, but you saw the presentation that Dr. Campos gave that wrote the paper and his colleagues from CableLabs. The paper itself is phenomenal. Dr. Campos gave a great presentation on it, but we're going to get into the paper in just a second. It gives a really nice history of how we got to kind of like the networks that we have today, as well as how we're continuing to evolve, and the kind of like the culmination is pushing fiber right into subscribers' homes. But there's a lot of great nuggets in this paper. We're going to touch on the highlights of it. And I think there's something in there for everyone that's going to be listening today. And as we go through, I see there's already some chat in the chat room, guys. Drop us questions. We'll try our best to answer it. And if you don't get your questions in, just drop us a comment in the messages below. We'll try to get up on there. But we're going to jump into this paper pretty quick here. So we'll get this up on the screen. I'll try to describe it for those who are listening to the audio-only versions of this presentation. So the paper itself, you can we'll have a link at the very end of this where you can download it off of nctatechnicalpapers.com. The paper itself is when Dr. Campos was giving the presentation, and you can see John's head, the back of John's head here, watching Dr. Campos give, you only get about 15 minutes to give the presentations, so it just does not cover all the great content that is in the paper itself. So if you want to watch the video, you want to watch this quickly, you can get it at techexpo.scte.org. You'll see the link down here. Watch it as quickly as you can because SCTE tends to take these down after about 2 months of them being up after SCTE Expo, and we're in the year 2024. So if you're watching it after this year, this link will probably be dead. The paper itself, though, I strongly recommend people take a look at the paper, and we'll have a link to download the paper at the end. This paper is a really, really good paper because I find it gives, it's like I said, it starts off with this background. And this background kind of gets into how HFC networks were probably, quite a few years ago. Some cable operators may still have this architecture around where we start off, with our head end. Our head end has a fiber optic cable that goes to the fiber node. This could be, and we're going to assume this is an analog fiber node today. Shortly we'll be talking about the transition from analog fiber nodes to digital fiber nodes like RPDs or RMAC PHYs. But from this architecture here, we see what, historically we have. Again, we still probably have a lot of cable plants out there today. Would be like a Node Plus 4, Node Plus 5, even Node Plus 6 architecture. What exactly does that mean? That means we have a fiber node, and from that fiber node, we go through multiple amplifiers. That's the N for the node plus, and the plus is how many amplifiers do we have until we get to the subscribers. So go through the node, we go through 1 amplifier, 2 amplifiers, 3 amplifiers, 4 amplifiers. That's our N plus 4 amplifiers, and then we have subscribers after that 4th amplifier. Typically what happens is the subscribers after the 4th amplifier, you're going to have some type of signal degradation in the downstream, and then of course the cable modems on these subscribers at the end of this 4th amplifier, when they transmit their signals in the upstream, those signals have to be amplified the entire way through this upstream, even through this last amplifier, until they get to the fiber node. So you may get signal degradation on the upstream in that signal path as those cable modem signals propagate back to the fiber node. And then once they hit the fiber node, they have to be converted from an electrical signal back to an optical signal, transmitted up through the fiber, all the way back to the head end where that CMTS is, converted from an optical signal back to an electrical signal so that the CMTS can receive that signal. And this is sort of the traditional N+4, N+6 head end that we see, still out there today. So,
all right, let me elaborate.
Go.
So I liked the paper and where he went with this, because the old saying, if you don't know history, you're doomed to repeat it, right? So you need to know the history, where you started. You got to take a step back from everything and say, all right, what are we trying to achieve here? Best MER, best speeds, customer satisfaction, right? Quality of experience. So he looked at that, I guess, holistically, look at the whole system, and how do we achieve that with the technology we have today? Where did we start? Is there some things we can make better? Where do we go? That picture you had of the N+4, N+5, even though it's node +4 and cascade, you could easily have 20, 30 amplifiers off of that node, because we're branched out all over the place, right? It breaks off a splitter, breaks off a splitter. So you can have a lot of actives feeding their noise figure in the upstream back to that one node. Right. So we talk about noise funneling, upstream noise. The one case where you pointed out the modems on the far end, farther away, could have worse response or degradation on the upstream is they have more probability of reflections. Right. Because they got to go through every one of those taps and everything back. But in regards to carrier to noise, everyone should have the same carrier noise ratio, because the noise coming from everywhere goes back to the CMTS.
Right.
And everyone should be hitting the CMTS at like 0, and the noise floor is what it is. So everyone has, in theory, the same carrier to noise ratio. But not everybody has the same MER, because one house that's farther away might go through micro reflections and what do we call it?
Echo cavity.
An echo cavity, right? And then if you're farther away, you're going to have many more echo cavities, because you have a tap, 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 amplifier, tap, tap, tap. So yeah, there's a lot more probability of issues when you look at group delay, micro reflections, things of that nature.
Yeah, and so we'll talk shortly about that KN connectors, but the things that often causes those echo cavities is in the outside plant. If you have loose connectors, if you have corrosion in amplifiers, if you have hardline coaxial cable that may have radial cracks in it or squirrel chews in it, or any damage to the outside physical plant. So the further away that subscriber is from the fiber node, the greater the probability is that as that signal from that subscriber transits through the network, either in the downstream or the upstream, that it's going to see those impairments in the outside plant.
And then in regards to the downstream, you could have cracks or little wrinkles in the outer sheath of the coax, and it's fine at 1 gigahertz. But once we go to 1.8 gigahertz, it might be a different story.
Yeah, and we're going to talk about higher frequency shortly.
Higher frequency is very temperamental.
So, all right. So we didn't talk about tap. So in the next slide, another critical part of that cable plant that we saw, in addition to the fiber nodes in the RF and the RF amplifiers, are the mainline passive devices that we call distribution taps. Distribution taps gives us the ability to tap off a small portion of the RF signal and send that down into the subscriber's home, as well as those RF signals coming from the modems get to come back up and be added back onto the mainline or the hardline cable. And in this image here, Dr. Campos in his paper talks about how we start closest to the amplifier at high value taps, and as we go down through the coax plant away from the fiber node, we go to lower and lower value taps. With the most common value tap being the 20 value tap. So when we talk about an inventory standpoint, cable operators should be buying more 20 value taps than they are the other value tap. So high value taps are deployed close to the node or amplifier, while lower value taps are deployed further away from the node or amplifier. And And John, I expect there are issues that happen with lower value taps than there are with higher value taps. Maybe you want to touch on some of the isolation issues we've talked about before.
I mean, if everyone had the same amount of noise in their house, a house attached to a low value tap has less attenuation. And at lower frequencies, the coax doesn't really provide much attenuation. So noise from a house on a low value tap is going to be worse than noise on a high value tap.
Correct.
So most of our noise problems come from houses off of the low value taps. Now, going back to your diagram there with the, many times you don't see any 29s or 26 taps. The first tap usually is a 23 because of our level issues on the upstream and maybe downstream and the tilt. So a lot of times that first tap off the amplifier or off your node there might be a 23. So I might see a 23 and another 23 and then a 20 and a 17. You get what I'm going there?
Yeah.
And then instead of going down to a 1411 tap, a lot of designs would have took that second amplifier and backfed a 23 and a 20. That way you don't have a low value tap in between the two actives. You understand what I'm saying? Like, you could use your mouse here and draw it. I wish I could move my mouse. You understand? Go to that first amplifier and you'd have a distribute. Yeah, that's the node.
So it depends on the spacing. It also depends on how many subscribers are off of each one of these taps, how many taps you have coming down here. And who typically makes those determinations? Does a technician determine that when they're out building this, John? Or, I mean, how does this all come to be?
Predetermined by hopefully they have good maps and they're using Focus or Load Data or some type of mapping software. And they actually walk it out properly, right? They're going to place it on the pole where that pole is supposed to be. And then that value is dictated by the levels they want at the house. So those levels are going to be dictated by the spectrum you're using, how much downstream I need. And then the problem I've always had with this design, taking a step back, this design was always based for downstream. Right. And then later on, we're like, oh, let's get upstream to work. And
we'll figure it out.
Yeah, we'll figure that part out later.
Yeah, I mean, oftentimes there's network planning groups that they design the architecture, they design the spacing, and then they tell you this value tap goes in this location, this next value tap goes in the next location, so that the value taps are predetermined. And then when the technicians are installing them, they may change the value tap in order to get the desired downstream power levels at the subscribers' homes.
Yeah, the problem would be is like the design calls for a 20. And that house is not getting enough downstream levels. So instead of fixing the problem, whatever's causing the problem, let me change the 20 value tap to a 17. But if you put that 17 in, now there's more insertion loss for the taps downstream.
Right.
So now it's just a domino effect. You're changing and going away from the design, and the design was there for a reason. If you're trying to mask a problem by just changing the tap faceplate, that's not a good thing.
There's a few questions in the chat room. Username redacted. There's that sexy beast. What's up, fellas? Good to see you. Username redacted. Thanks for joining us again. Grab a sandwich. Good to see you. Alternate title. Cable writers choose to pump huge money into old coax plant instead of fiber. Glad you have that positive mental attitude as always. Grab a sandwich. And he says he can't imagine what it's like to be a maintenance tech. Sounds like a major headache. Got you there. Never in my truck. Oh, and username redacted is back in my truck looking at P&M impairments, tracking 2 ECs right now. No, and he says, no, I worked in service for over a decade. Never considered moving into maintenance. Now that I'm in maintenance, I would never go back to service. I love it. Good to hear that. It's a Band-Aid, username redacted.
I used to have a joke. I'm like, it's okay to have a Band-Aid, but pure mummification is not good. You're wrapping the whole thing in gauze and you make a mummy out of your entire system. That's not good.
If you can't fix it with duct tape, I mean, what else can you do?
If you can't fix it with duct tape, you didn't use enough duct tape.
That's right. You need to get another case of duct tape. All right, so this next section in Dr. Campos's paper, he covers power versus efficiency. So in the figure on the left, it shows increasing CNR as you go from 16 QAM to 64 QAM to 256 to 1024 to 4096 QAM. And in each case, your power from 16 QAM to 64 QAM to 256 QAM, you have to increase in 6 dB steps. And then going from 256 to 1024 QAM, you have to increase your power by 7 dB. So your quadrupling the amount of power or more from your cable modem in order to support those modulation increases. And in doing those modulation increases in the image on the right-hand side of the slide, we're showing that your spectral efficiency, and spectral efficiency just means how much capacity gained from a data throughput standpoint. Your spectral efficiency in going from 16 QAM to 64 QAM, you get a 50% spectral efficiency increase, which means your data capacity, your data throughput doubles. But from going from 64 QAM to 256 QAM, your spectral efficiency or your data throughput only increases by 33%, even though you had to quadruple the power that you had going through, or quadruple your CNR improvement. From going to 256 QAM to 1024 QAM, you only get a 25% data throughput improvement. And going from 1024 to 4096 QAM, where you had to improve your CNR by 7 dB, more than quadruple your power, you only get a 20% spectral efficiency improvement. And so I think Dr. Campos made he posed a really good question here. He said, this efficiency behavior prompts the question, is it worth it to increase the power by a factor of 4 to achieve a 20% increase in efficiency? And then he went on further in the paper, and that's why I really encourage everyone to read this paper, is would that factor of 4 increase in power, would that be better off put to increasing your RF bandwidth? Give you more RF bandwidth, because with more bandwidth, we can pump more data through more bandwidth, rather than trying to clean up the plant and optimize the plant so you can achieve 4096 QAM. Maybe we just give more bandwidth and maybe you'll get 4096 QAM, or maybe you'll just get 1024 QAM or 256 QAM, but we just allocate that towards more bandwidth. And I thought that was a really intriguing optimization, particularly because I'm working with products that work to get you 4096 QAM. It's an interesting observation, John.
I think the conundrum, I think that's a good word for it, conundrum. Many people are pigeonholed, is that a good word for it, or hamstrung on their spectrum. They only have so much. So I get what he's going at is, do I have to have a better performing plant and allocate better MER to get 1024 QAM or 4096 QAM, when if I had spectrum available, what if I just allocate more 2 channels at a lower MER and they're both at 1024, but I'm getting more overall speed? But the problem there is the spectrum, right? So
that's smaller spectrum when you're allocating 2. You're saying 2 small channels, smaller spectrum, right?
No, I'm saying 2 channels, 192 megahertz wide.
Okay.
It's eating up more spectrum than 1 channel, obviously.
Right.
But you're running the 2 channels at 1024 QAM versus trying to run 1 channel at 4096 QAM. Because the 4096 is only getting you 20% more speed, but the 2 1024 QAMs are getting you double the speed because you doubled up, sort of. But I think that the problem is, like, if I had the spectrum, I would use it. But they might not have the spectrum to use in the first place.
Yeah. And I think if people put 2 192 megahertz channels, they're still going to try to run a 4096 QAM.
I agree. I mean, why not? And that's the whole beauty of the PMA stuff. The what's it stand for? Proactive
profile management application.
Yeah, profile management. It's smart enough to keep track of some of the parameters and change automatically, right? So it's not like you're hard setting it. Go back to that graph real quick. The only nuance there, I would say, is when you go from 256 QAM to 1024.
That's a pretty big jump, actually, because you have 512 in between there.
Yeah, but 512 is not a square constellation.
Yeah.
256 is 2 to the 8th. 1024 is 2 to the 10th.
Yep.
So he's talking about square constellations, not these oddball constellations. Right. It's a symmetrical constellation. But if I was going from DOCSIS 3.0, 3.1 or DOCSIS 3.0 to 3.1, it would be a 0 dB power difference because we gain 6 dB in robustness with OFDM.
Right.
He's showing OFDM completely, right? He's saying if you
there's
OFDM,
no SC QAM here. This is an OFDM or OFDMA possibly discussion.
Yeah, I'm just throwing that little nuance in there. It's like if I went from 3.0 single carrier QAM to 3.10 FDM, that 256 QAM, 1024 QAM is a no brainer. It's
Yes.
really the same. It's the same cutoffs.
So I think this is just, again, food for thought for people who are out there looking at how they're going to allocate their spectrum, what they're going to do with it. And also they have to realize they have to make sure they have the power reserves on their devices to do that increase. Okay, next part of this in Dr. Campos, and I'm kind of following section by section in the paper. So if you're following along in the paper, that's exactly what I'm doing here. This next section talks about, we really were in the node plus 4, node plus 6 before. This talks about, okay, now we start to segment the node before. We're getting in the fiber segmentation. How did we get to those really long cascades into a node plus 2 network, which a lot of operators are going to. We're starting to push fiber closer to the home in this next slide. So here we are with our original fiber node that we had at the very beginning of the presentation. This just becomes an optical distribution node or optical distribution system where we still have that original fiber coming in, but now this becomes a fiber splitter. Or if we have multiple fibers, we just split out from here. And now where we originally had RF amplifiers, we drop in fiber nodes to each of these amplifier locations. And now these fiber nodes are converting the optical signals. So this was originally a coax coming down here, and those optical signals are converted to electrical signals in the fiber node. And if we look at the same path before where we had node plus 4 in this section of in this network, this is now node plus 2 going out to this last cable modem. So from, when you talked before about a subscriber quality of experience, this subscriber out here on the very end of this leg, their quality of experience, their everything should improve from them. Their downstream signal qualities, their upstream signal quality, that all should improve because we've reduced the amount of coax going to them because we've pushed fiber deeper to that subscriber. In this node plus 0 net or node plus 2 network, we've reduced the amount of amplifiers. In theory, that's the concept.
Yeah, I mean, obviously we're trying to get fiber as deep as possible, but there's still that monetary side of it that it could be node plus 0, it could be a node inside of a tap, but even getting rid of the coax cable from the tap into the house can be cumbersome.
Yes.
Could be difficult. It's a timing issue. It's underground. It's meeting up with the customers to make sure they're home that you can get in there. So yeah, there's still logistics that have to occur there. And I don't disagree. Fiber to the home would be the way to go if you can afford it. I mean, there's still money that comes into play.
Correct. So username redacted says, give me more spectrum, keeping SNR in the low 40s in order to support 4K QAM in all our nodes. Makes my head hurt. Yes. Well, it's the objective. And Peter Krupel, hi all. And username redacted says, hi Peter. So.
He said howdy. I said hi.
Howdy. So we just saw how we got to node plus 0. Then the obvious next step is getting we just saw how to get to node plus 2. Now the obvious next step is going to node plus 0, where there are, we'd like to say no RF amplifiers after node plus 0. So, the fiber node, we've pushed fiber all the way to the last RF amplifier. So ideally we just have a fiber node, and everything after the fiber node are subscribers. So there's no amplification after that. In some node plus 0 networks, we may still put a line extender if it's going down an alley and we still have to feed some subscribers. But still the concept with a node plus 0 network is nothing after the fiber node. Again, that pushes fiber even closer to the subscribers, and it should, again, improve as username redacted is asking, get that SNR up for all subscribers and allow us to do 4K QAM for everyone if that's the objective there.
I mean, smaller segmented areas are easy for troubleshooting. There's less noise funneling, obviously. But yeah, it's just there's a lot more fiber, so you also have to come up with a lot more 10 gig circuits as well.
Yep.
Because if you're running 10 gig to each fiber node, now it's a lot more 10 gig segments. Um, so yeah, I mean, you trade off one thing for another, but we are trying to get fiber deeper and deeper. And then into the house, some of our biggest problems now are house amplifiers because we have no control over it. And so they're buying their own and then putting a house amp in, and you don't know if it's passive upstream or it has no upstream at all, or it's active upstream.
Yeah, so we've kind of implied, and this slide is still making the assumption that these fiber nodes are optical fiber nodes because we're showing the optical transmitter and receiver here. In just a moment, we'll talk about digital networks. But yeah, I'm sorry, it's analog.
They're all optical.
It's all analog nodes. But that being said, we Dr. Campos in this section of it does start to talk about how much data each one of these nodes is transmitting across it, and he's suggesting it's approximately 10 gigabit per second per node. And so as you get, we're looking at 12 nodes in here, so the aggregate of all of these 12 nodes that's coming back into this head end is roughly 120 gigabits per second. That is not true. It's not a trivial amount of traffic, because you were talking about the need for a 100 gigabit per second digital link, and we'll talk about that momentarily. But that's not a trivial amount of traffic for this 100 homes passed or 500 homes passed. So if anyone's not familiar what HHP means, when we say 500 HHP, that's 500 homes passed in this network. Now that doesn't necessarily mean that this CMTS or this network is actually connected to all 500 homes, but it means we have 500 homes that we have the opportunity to be connected to. We may only be connected to a certain percentage of those homes. That's just the market opportunity we have, and that's a common term that we used in networking when we say how many homes passed, and then what's our take rate. Maybe our take rate's 80% of that. So that would be how many homes. 80% of 500 would be how many would be connected to.
Yeah, and technically, I think it's households passed. Hence
households passed, yeah. I could be wrong with that. Another initialism that I'm screwing up.
But it's funny too, is a trade-off of, do you provide more aggregate speed for more people to share, or do I have to provide higher speed for more peak rates? Because if you segment the node into a really small area, and that one small area is just a couple houses, why am I dedicating 10 gig to one node that doesn't need it? Yes. Unless I'm selling 5 gig service, or you know what I mean? Like if I'm selling a high peak rate. So then the question is, if it's not that many people, but they require a higher peak rate, it might be better to keep the area bigger so they can share a bigger pipe. So
well, and that's one of the, so why are we driving node sizes smaller? I mean, one of them is to improve quality of experience, quality of service, because you have less homes on that node. But another one is because, to your point, and the amount of traffic that subscribers are using today keeps growing and growing and growing. So we have to reduce the number of subscribers on that node so that we can manage that traffic, particularly during times like peak times. So that drives it. So username redacted says we've upgraded to 1, so I'm assuming that's node plus 1 in there. So Grab a Sandwich says, I had a service call a few days ago for intermittent service. The node was upgraded from analog to digital the day before. That's not the way it's supposed to happen. So yes, we have that. Username redacted said, I can't wait to see what happens when we upgrade from older, more neglected markets to 1.2 gigahertz, considering the amount of old splitters, 1 gig house amps, and dated weather RG59. We're going to hit on that in just a moment. Not on the house amps. House amps we've covered before. They are a problem, but the higher frequencies we're going to talk about in just a minute. So exactly, username redacted. The chat room is active today. Peter says not all segments will burst at the same time, so 120 gig may be greater than 1% of the time. Yeah, that's actually good. And I think you were touching on that, John. It's like some areas of the plant are going to be maybe greater than 10 gig, where other areas of the plant may be sitting at 500 megabits per second. It's very demographic specific, which means just depends on the users.
Yeah, and that really drives what we call oversubscription, right? the fact that everyone's sharing it, but not everyone's peaking or bursting at the same instant in time. So the bigger the pipe is, usually the more you can oversubscribe it.
Right.
So that 12 segments, 12 10 gig segments might all come back and bottleneck to a 50 gigabit per second.
At your core.
Yeah, because you're not going to do 10 gig on each one of them at any time. So the bigger the pipe, 50 gig, 100 gig, whatever, you could oversubscribe it a lot more.
Yep. All right. So next up, more spectrum. So, we talked about we can add more channels. We can increase the modulation. We can reduce the number of subscribers on the node. The next thing is when we look at DOCSIS 3.1 or DOCSIS 4. DOCSIS 3.1 takes us to 1.2 gigahertz. DOCSIS 4 takes us to 1.8 gigahertz. DOCSIS 5 takes us to 3 gigahertz. So really what we're talking about here is that slow evolution. I mean, at one point, our cable plants continue to evolve from 250 megahertz spectrum to 350 to 450. When I started in cable, we were just hitting the 750 megahertz mark. Then we went to 860. Then we've seen it go to 1002 megahertz. DOCSIS 3.1, as I said, 1218 megahertz, 1794, which we call 1.8 gig. And then DOCSIS 4, DOCSIS 5 takes us higher. I put a marker down here on the x-axis. So we're showing an x-axis here and a plot going from 0 all the way up to 7.5 gigahertz. And I have a little marker down here showing we are here at 1.2 gigahertz today with DOCSIS 3.1. And we have a bunch of lines on the graph here showing from RG6 coax, RG11 coax, half-inch, 0.625 inch, 0.75 inch, and 0.875 inch hardline coax, and we show different cutoff frequencies. So the cutoff frequency for RG6 is 29.1 gigahertz, and going all the way up to, or all the way down to 6.6 gigahertz for 0.875 inch coax, and we can see the different attenuations associated with each coax type in dB per 100 foot. Basically, what this is showing is coax goes all the way out to past 7.5 gigahertz up to 8 gigahertz. You just have increased attenuation, but there's no cutoff with our different coaxial cables that we have out in our HFC networks. They're going to support high frequencies. They're just going to have higher and higher attenuations. It's not exactly linear, but I mean, on the log scale, the lines look sort of linear-ish. But there's really no critical issues that's going to stop us from going to higher and higher frequencies with coaxial cable. It's pretty decent. It's sort of it's a wave.
What I find interesting is, well, one, we don't really have trunk cable anymore, so you don't see much 0.875 or 0.75. There might be some 0.625, but most of it's half inch for distribution, right? Bridger amps and distribution. So most of it's half inch. What's interesting is the bigger cable has less attenuation per 100 foot, but the bigger cable runs into a secondary issue that cuts off the highest frequency it can go to. Yes. Now, granted, this graph is way out there.
Yeah.
And by the way, your line's not pointing at 1.2; it's pointing at
Oh my gosh! Yeah, you're right. I just noticed that.
That line needs to be pointing up a little bit, but
it should be right up here where my laser pointer is.
Yeah. But that's a small little piece of what Alberto is showing on this graph, right?
Yep.
So I call it a pipe dream, tongue-in-cheek pipe dream. To be able to go out that far. He's just showing that the coax is capable of going way far out in spectrum and frequency, but we all know the attenuation is just astronomical.
Yep.
Once we get out, we deal with problems right now at 1.2 gig. Can you imagine going out to 5 gig?
Yeah. We're going to have to respace everything if we do that.
Yeah. And then, like you said, might as well do fiber at some point.
So it looks like cable operators are doing upgrades, as Longshot 1056 says. So the upgrades we are doing have been such a pain. We are replacing only the amps, removing line EQs, and doing internal tap EQs. Problem is, all the old connectors and DCs are causing roll-off, which we're going to talk about that in just a minute too. That and old MC2 cables, MC squared cable in some areas are problematic too.
Let's get that person to respond. I believe the MC squared cable has a known suck out right
Is
about.
that the mold spike that
Yeah, yeah. It used to be at like 550. Isn't it like 1.1 gigahertz? Or
it's
they
not good
changed the
for
mold
going
limit.
out the 1.2.
They just shifted it up, and it was outside 1 gigahertz, so no one saw it. But now that we're going 1.2, people are seeing it again. So yeah, it was a no. It was such a tight. It looked like a filter
Yep.
because it was evenly spaced
They
discs.
they have
Or
these
the
little discs in
bridges.
the MC
Yeah,
squared cable that keep the center conductor basically in the center of the outer conductor, and that created a number of issues.
yeah.
It's non-ideal. Um, Here in our plant in Denmark, and we have 2,500 modems. It is Friday night, 8:30 p.m., peaking 7.9 gigabit per second right now with 16 RPDs. That's awesome. So thanks for that. And yeah, let's get a hot dog. Denmark hot dogs are the best in the world. All right. So next up, username redacted. Yeah. So, oh gosh, I'm sorry. They have lots of MC squared still in use. Many P3.5 connectors found installed in MC squared cables. Impairments abound. I'm guessing the last was just trying to ensure job security. Same here. Well, you got something to do. Gotta keep yourselves busy. It's better than the alternative. So next up, we got tap housing. So Dr. Campos did talk about the tap housing issue that we just, I think username redacted was just talking about, and so Figure 9 highlights just that. So the dotted line here, we can see one of the older tap housings that just starts to cut off just around 1 gigahertz. And then you can see the insertion loss it's kind of like a brick wall. It drops all the way down to around minus 10 dB of insertion loss there. And then up around 1.8 gigahertz, there's another significant drop off where it goes almost down to minus 30 dB of insertion loss. So that's one type of tap housing. And if you have those in the plant, there's just no way you're going above 1 gigahertz. The dark blue line, that shows a new tap faceplate that is a 2.75 gigahertz design. So it goes it's nice and flat, way, all the way out to at least 2.75 gigahertz. Well, actually, we're showing all the way out to 3 gigahertz. That new tap faceplate is super, super flat. So just replacing the tap faceplate gives you a tremendous difference in the insertion loss there.
What do you think about it? When you buy something, you're buying it with a spec out to 1 gigahertz. So you think anyone's going to spend time tweaking it out to make sure it goes further? So it passes the spec at 1 gig, you throw it back in line and ship it off, right? So they were never meant to go out that far. I think the interesting thing is the housings were never meant to go that far either, but I think the housings do. Right, so they're showing that they can maybe just change out the seizure screw or change out the faceplate, and that's all that's really needed. And the housing and connectors might still be good all the way out to 3 gigahertz.
Yeah, so when I was an RF engineer designing 860 megahertz amplifiers, we would design them to go out to 870 megahertz, 10 megahertz beyond the spec, and they would drop off. And then in production, it was the same thing. The people that the technicians that were aligning the amplifiers would align them out to 870. They probably could have gone further, but the spec was 860, so we did them to 870 and shipped them. So all they had to do. Dominic says, if you go to 3 GTS, doesn't interfere with a C-band spectrum cable company still use SIP-PAN to get their channels. I'm assuming he's saying if you go to 3 gigahertz, doesn't interference with C-band spectrum used. I'm not sure what the SIP-PAN is to get their channels, but I'm thinking he's talking about 3 gigahertz interfere with other signals out there.
Anytime we go a different spectrum, if it's not an enclosed system, like cable should be enclosed, we have ingress and egress. So we definitely got to look at what's in the air at different frequencies to find out what's the potential interference.
Yeah, it's the same rules apply. We can't interfere with LTE. We can't interfere with airplanes, and we won't be able to interfere with like Wi-Fi signals that are in the 2.6 or 2.5 gigahertz band.
5 gigahertz, 3.5.
Yeah.
Yeah.
So same rules apply. We got to keep our plants clean and keep the signals in and the signals out. So yeah. Username redacted lab, not keeping up there. So yeah, long shot says we stop at 1 gigahertz, so we don't have that yet, but it's such garbage cable that if water gets in at all, the whole segment is trash. And we know that once water gets into coax cable, high frequencies really don't like water, so it just trashes all the high frequencies. Trainwreck says, at scale, that would save dollars if only housings need replacing. Yeah, if we could just replace just the tap faceplates and the RF amplifiers, but unfortunately, yeah, a lot of times we do have to replace the RF housings with amplifiers, and sometimes even with taps, you have to replace the housings on the taps as well because the housings weren't designed to support the higher frequencies. All right, moving along, we said we were going to talk about KN connectors. These are your regular, KS connectors. These are your regular connectors that go into amplifiers, or maybe it's just a splice that you're doing out in the outside plant. You know, we think these are really simple connectors. You can't do anything wrong with them. The connectors themselves, even if you get them perfect, Dr. Campos talks about these in his paper where the dark blue line here we're showing a perfectly mated KS connector has a slight dip at around 2.5 gigahertz. And then he shows multiple connectors, 2 splices. Here's the red line. When they're kind of paired back to back, you start to get a ripple, and then 3 splices, and these are all done, these are properly connectorized, meaning that no craftsmanship, no errors were made. We didn't, overcore them or over tighten them or under tighten them when we put them together. 3 splices put together, they start to, these ripples start to stack up. So when we look back here at the 1.2 gigahertz, or even we think about going to 1.8 gigahertz, we start to see some variations that now we think about putting, many of these KS connectors together. Even doing it right, we're going to see some perturbations, some things that are non-ideal from an insertion loss standpoint. And maybe we have a technician that doesn't tighten it down all the way, or maybe we have a technician that over tightens and creates a little radial crack at the main hardline connector going into this KS connector, and things now start to get really ugly. So when we start thinking of higher frequencies, craftsmanship becomes really important, and looking at this really shows us a picture that things can and will get ugly in the outside plant. Going to node plus 0 will become more important at high frequencies, or at least node plus 2 will become more important at higher frequencies. And this is a really good indicator as to why. So John, your thoughts on this?
Yeah, I think the graph would have been a lot stronger type of visual if they did 1 or 2 dB per division.
Yes,
that's 5 dB per division, so it doesn't look that bad. I used to say it's all relative, right? When I do my sweep traces peak to valley, do a 10 dB per division, it looks nice and flat.
Oh, that's perfect plant, 10 dB per.
Go to 1 dB per division, open that thing up, and see how bad it is, right? So it's all relative of what your graph is showing. But yeah, I was looking at it, and 5 dB per division doesn't look that bad. But if you did 1 dB per division, it's probably like a 3 dB swing.
The net is a little over 5 dB with just going through 3 connectors.
Yeah.
So
that also really pushes me to explain that not having to change out housings is paramount, because if I have to cut a housing out, you cut the cable a little bit short to cut it out. Now the next one doesn't really fit; it doesn't go together. So you have to buy either an
extender.
They made a 9-inch, or you have to buy an extender or another connector or another splice. And the more we have to do, the more it's going to get worse and worse and worse. So it's
and we've both seen plumbing on amplifiers where you have like multiple connectors stacked together to make it fit. That's non-optimal.
Because that graph was showing cascaded splices. I'm like, who would cascade splices? Well, believe me, it does happen.
Yeah.
You see it.
So Dominic's following up on the discussion later about he says, sorry, voice to text. They still get their channel from C-band. That was going into the interference at 3 gigahertz and C-band and stuff. But again, same rules apply. So next up, in Dr. Campos's paper, again, read this, everyone's great information, but he did a nice discussion on why, another way that we can get more capacity in our network is transitioning from optical amplifiers, which is on the right-hand side, to digital amplifiers, which are either RPDs or remote PHY or remote MAC PHY. And so just quickly discussing that. The analog on the left-hand side, the analog fiber node, that's where we have an optical receiver. The optical receiver takes in the downstream, that takes our optical signal on the fiber and it converts it from light into an electrical signal. And that electrical signal then is amplified, equalized, amplified again, goes into our diplex filter, and then is put on our coaxial cable and sent to our subscribers. And then in the return path from the modems, we have the upstream transmission coming from the modems. They get combined if you have multiple inputs coming into the amplifier. They go into some signal conditioning. They get amplified, converted from electrical to optical, put back on the fiber, and then they get shipped back to the head end, to the optical receiver in the head end. Compare that to the digital node. The digital node, instead of having an analog optical fiber coming in, it has a digital optical fiber coming in, which we call a CIN, C-I-N. And then that goes into a digital component in the fiber node. If you notice, the rest of the fiber node looks pretty similar, but that digital component takes the CIN in, it takes digital data, converts the digital data into an electrical signal. So now that electrical signal is the same as the electrical signal in the fiber node on the left-hand side. It gets equalized, amplified, goes through our diplex filter and onto the subscriber, and then the cable modem signals coming from the subscriber goes back into our diplex filter, and then that goes into our RPD, our remote MAC PHY node, and then it gets put back onto the CIN and gets shipped back up to the head end. So that's the major difference between the analog fiber node and the digital fiber nodes.
So the analog fiber node, I used to say, another terminology was, I use myself, intensity modulated. You're changing the intensity of the light. So on an analog fiber node on the upstream, RF is energy. RF is current, amperage. When that hits the diodes or whatever needs to go into the analog fiber node on the upstream, you're changing the intensity of the light. And if you change it, and no matter how high you go, also have to go low. So it's high and like a sine wave.
Yeah.
So when you overdrive it, we call it laser clipping. And ironically enough, it's not just the overdriving, it's the underdriving where you have a certain bias current for the laser. And if it has to go lower than low, it shuts off.
It doesn't turn
on. So when it shuts off, now you have distortions. So that's part of laser clipping is overdriving / underdriving, because they go hand in hand. And then you have laser clipping, you have distortions. So we know that the more power you put in, the worse it's going to get. So the more activity I have on the upstream, more traffic means upstream's always on. Because normally it's not always on, right? Upstream's bursty. But now we have more traffic, so it's more traffic.
It's more on than it's off now.
Yeah, you're more on than off. But if you open up the spectrum, that's even more energy. So you go to 204 upstream, that's even more spectrum, more power, more higher modulation schemes from OFDMA. So to do that on an analog upstream could have more laser clipping. So that's why I've always been a proponent of switching over from analog fiber to digital fiber, because now it's just the light is not intensity modulated, it's just on, off, on, off, on, off. That's digital, right? 1 0, 1 0, 1 0. And that's a lot cleaner. It's better MER. It doesn't have laser clipping. Yeah, that's all kinds of... It
improves quality of service to our subscribers. It gets us to that 41 dB MER that that they're asking for in a chat room, so we can do 4096 QAM.
Yeah, you're only as good as what you start out with analog fiber link. It used to be on the downstream, you might only get like a 45. Now on the downstream, you might get with a 50. Yep. Because you went to a digital link.
So Peter says at 1.8 gigahertz, node plus 2 is smaller than node plus 2 at 1.2 gigahertz, or you need more gain in the amplifiers.
It turns out to keep the same spacing, they've come up with better technology that we didn't have to respace our amplifier housings. We keep them in the same spot on the same poles, but you definitely need more gain. so that you can overcome the loss in the coax between those amplifiers. So they went from GaN, gallium arsenide, gallium nitrate, to gas, gallium arsenide. There's all kinds of different technologies they're working with the silicon to get better performance and better levels. So you can drive the heck out of a hybrid amplifier, but then you get more distortions. So there's a trade-off there, right? Like, how much can I really drive this thing before I get into composite intermodulation noise?
Yeah. So Longshot 1056 says, going from BTDs to MBT120s, I've seen a 12-inch extension to a 3-inch on the input due to size differences and people not willing to take connectors apart and just cutting them off. So just changing the amplifier housing can cause problems in coax spacing. I'm going to guess the first name is pronounced Talk, but I could be wrong on that, so I apologize. We need a phonetic pronunciation of it. At Peter Krupel, maybe we can have John tell a bit about the 6-watt amps. John, do you have any information on 6-watt amps?
No, and I'm wondering if he's mentioned like the Technetics distributed gain architecture or the diplexer-less amplifier.
Yeah.
Yeah, I don't have anything off the top of my head to talk about it.
Okay. Corey says, I can't wait to start helping my company deploy high split, but the implementation dates keep getting pushed back. Love the show. I have learned a lot from watching the VOD. Thank you, sir. At Corey Maxwell, high split in the HFC is not that bad, but what has been disappointing is the time to change the data splitters at the subscriber homes. Yeah, getting into subscriber homes is problematic sometimes. They are not as easy. All right, let's talk train wreck. How is node power consumption analog versus digital? Negligible or difference? John, my experience is the digital node power consumption is significantly more.
Well, I mean, you're taking the brains from the CMTS and the head end and putting it in the node.
Yeah.
So you have
and our MAC-PHY is
you have the Broadcom or TI chipset demodulating signal inside the node. So you have heat sinks you got to worry about, right? You got to make sure the heat is dissipated properly. So the fins on the node, even the node is not sitting a certain way where the heat can't actually rise up and get out. So it's not trapped. You got RF shielding that has to occur, and the power to power up everything, and even the weight, right? I think the weight of a node is under 50 pounds, right? If it's over 50 pounds, then you have to have like a bodybuilder.
They have to have you come out and install the node for them.
Literally, there is a spec. It needs to be like 49.5 or under 50 pounds. The industry wanted the nodes to be under, what was it, 50 watts?
It was 50 watts, but I think they decreased it to 85 watts now.
With the GAP node,
yep.
The generic access platform, I think they increased it, right? So you could put all kinds of other stuff in the lid and all that. But yeah, we with technology, almost like Moore's law,
it just keeps going up and up and up.
Faster, yeah, we get faster. And with everyone trying to go green, it is getting a little bit cleaner. When we said go analog to digital, like, oh, you're going to save so much power. Yeah, you save a lot of power in the head end, but you are putting some of that power out in the field because the nodes now have more complexity to them.
Yep.
But with the newer technology, that's kind of been hovering almost the same. So either way, it is better to have a digital node out there than analog nodes. You get rid of all the RF connectors in the head end. You're really moving the RF connectors out into the field. The only thing in the head end is the fiber connectors.
Yep.
So it's all optical.
Yeah. So, and Peter's saying until the last subscribers change, the low OFDMA channel has to be 20 to 64 megahertz. And I almost wonder if that's not because, Peter, I'm assuming you're in Europe. You probably have house amps that subscribers have that stop at 65 megahertz due to the diplex filters. I wonder if that's not part of the limitation you have. Raymond says single outlet in home solves a lot of issues. Very true. You got a single outlet, you have nothing in the home where you have other cables going around. So always a good recommendation.
I mean, you could promote, say, a gateway, right? You go
a home gateway, terminate.
And the gateway is Ethernet and Wi-Fi. There's no RF in the house at all. You know?
You're vibrating like crazy there, John.
I know, that was my cell phone.
And Longshot says for
my Australian didgeridoo or
Longshot says for 1.8 gigahertz, isn't the tilt requirements to maintain levels over distance going to cause MER issues on the low end? So they do different things with like a staggered tilt. Dr. Campos talks about some of that in his paper. He also talks about moving modems based on different distances from the fiber node. So, if the modem has a lower MER, we'll put it at a lower frequency. As it has a higher MER, we'll put it at a higher frequency. We don't cover all that. There's a lot of other cool things in Dr. Campos's paper specifically addressing that comment. I'd recommend you read his paper. He covers that. So yes,
I'd like to elaborate on that too, because I think it's an interesting idea. It's just more complexity, which goes against my KISS principle. But if we have AI, machine learning, and something that can do that smart thinking for us, then we can look at a house with historically low MER and say, yeah, he's really having a hard time with locking on upstream and downstream at these frequencies. So let's relegate him to frequencies he's good at.
Right.
And then I know he'll get better MER, which means that PMA can give him a higher modulation scheme. The other idea is if you have higher frequencies that rolls off, and at the high end of the frequency, it rolls off its bad MER, you're not going to get very good modulation because low MER.
Right.
Could you take power from those channels and allocate them to frequencies that have a better chance of running a little higher MER? So instead of us saying, I'll give you an example. On the upstream, we set the CMTS to 0 dBmV. Every upstream channel that comes from your modem wants to hit the CMTS to 0. What if I told you, let's set channel 0, that's at the lower spectrum, to +6? We're going to make the modem transmit higher at that lower frequency,
where there's more noise.
I know there's less attenuation at lower frequencies. So I have the oomph, I have the power in the modem to do it. So let it run higher on purpose, hit the CMTS higher, better MER, and let PMA say, hey, man, you're a candidate for 1024 QAM.
let's blast through.
Yeah. And then at the higher frequency, say 396 upstream, if we ever get that route, or even 204, you say, well, I know there's more attenuation. It's going to have a hard time. Maybe it's going to be relegated to a low MER anyway and a low modulation scheme. So that's where I'm going to steal the power from. So on the CMTS, I'm going to set it to -3 on the CMTS.
Yep.
So channel 0, hit it at +6. Channel 4, hit it -3. Yes, it's going to look weird.
It's like an upside down world all of a sudden.
Yeah, but you're doing it on purpose. Yes. You're robbing Peter to pay Paul. You're stealing his energy and giving it to somebody else that has a better chance of getting a better MER. Yeah, it's more complexity. I hate that idea, too, of more complexity.
That's okay. Grab a sandwich is cracking me up. Sure hope John gets a better mic. His echo cavity is pretty high. All right, F connectors. So Dr. Campos covered on upgrading, so he talks about, we've been using F connectors, I did not realize, since the 1950s. Do we need to upgrade F connectors to support higher frequencies? And I mean, I think that was an interesting question. And now we have the answer. So he looked at F connectors from 0 all the way up. I can't see underneath your head, but it's way past 12 gigahertz. And really what we see is F connectors are good to about 6.5 gigahertz. They only have about 1.5 dB loss at 6.5 gigahertz. They have some frequency ripple on there, not too terribly bad. Like you said, the scale here is 0 to -3 dB in that first bar. Little bit of frequency ripple, not something I would get too terribly worried about, but there's no frequency ripple up to 4 gigahertz. So that F connector probably, it's not much of a connector really, because it just this center of the coax comes through it, but that darn F connector is good up to 4 gigahertz. Remarkable. So the F connector is not going to limit us from going to higher frequencies. I think that answers our question.
Except for craftsmanship.
Yes, you got to do a good job. Use compression fittings. Do a good job putting the F connector on. Do not scrape the center conductor and impact your high frequencies, as we've talked about before.
It's funny about the F connector. A little trivia there. I believe it was the name was coined by a guy whose last name started with the E. So I'm like, why do they call it the E connector? Why do you call it the F? And then some people say it's because it's the freaking connector.
Yes, but it's freaking good. Keeps working in higher frequencies. I think it's one of the last sections we cover here. We'll cover this quickly, but this really talks about how DOCSIS can really be extended much, much more. probably more than what the CPE will even do. As we look at DOCSIS 4.0 today, we can do 8 OFDM channels at 192 megahertz. That covers a little over 1.5 gigahertz. If we do 16 OFDM channels at 192 megahertz, that takes us to 3 gigahertz of occupied bandwidth. 24 takes us to 4.6 gigahertz of occupied bandwidth, and 32 OFDM channels takes us up to 6.14 gigahertz of occupied bandwidth. And when we talk about like DOCSIS 5, what the goal is of DOCSIS 5, that's 12 OFDM channels of 192 megahertz. That would give us 20 gigabits per second of capacity in the downstream. and if we had a cable modem, and that's kind of the general discussion of this section 3.5.2 of Dr. Campos's paper, we probably will be challenged to get CPE that could lock to 12 OFDM channels at 100. That's going to be the goal of the industry, is to get modems that can lock this many OFDM channels. But going back to like what you were talking about, John, is we'll have that capacity out there. Modems closer to the fiber node will lock to the higher frequency OFDM channels. Modems further away from the fiber node will lock to the lower frequency OFDM fiber nodes, because they're as you said, they're going to have lower MER. And that's the cool thing. We're going to have all this capacity. They can lock to more OFDM channels. We could get 20 gigabits per second if we want it. I think the question will be is whether or not the cable operators go to DOCSIS 5, or cable operators say, hey, it's time to move to fiber directly to the home. And that just becomes a matter of timing. The thing is that's the cool thing about DOCSIS, the cool thing about HFC networks. Cable operators will have options. They can do 20 gigabits per second, or they can say, I'm just going to go to fiber and do 20 gigabits per second on fiber. So
Agreed.
Lots of options.
And fiber seems to be the push for symmetrical speeds too, right?
Yes.
It's easier to get symmetrical speeds.
Yes.
I do like the 3.1 plus 3.1 enhanced, whatever the terminology is, word du jour, or 3.1. What is the tuner inside those? They're good for 6 or 7.
It depends on depends on the chipset.
Yeah. I mean, 3.1 currently is only 2. 2, right? Yeah. Two downstream OFDM and 32 single carrier QAM. But the newer ones we're hoping that the industry would push, which they are now doing, the 3.1 plus or whatever they want to call it. I think they're good for 6.
Yeah, and I know some operators right now that are running 4 OFDMs in a downstream. I don't know of anyone running 6.
Because if you have the spectrum, you could, if you had enough spectrum for 8, you could do 8. Knowing that your CPE can only do 4, but like you said, now you could do like a load balance for OFDM. You could have some on this 4 and some on that 4.
Yep.
And then when technology comes around that a new chip that can decode all 8, so be it.
Grab a sandwich. No OFDM for you. The soup. We know what the soup is. All right. Always fun when a brand new F81 turns out to be bad. Yes. Bad connectors. Hey, Hunter. And don't forget, all F connectors have to meet SCTE ANSI specifications. Good suggestion. So we grow, we refine our standards, and continue to keep us on the cutting edge. Good to see you, Hunter. Thanks for joining. So finally, we covered a lot of things in Dr. Campos's paper. We definitely did not cover everything in there. We had a whole hour. I think we've gone over the hour to cover his paper. I still have some other suggested readings for people in the paper in this very last slide. Section 3.5.5, Dr. Campos talks about holistic management of the entire spectrum. Section 3.5.1, he talks about high transmit power and higher dynamic range, gets into total composite power, if any of you are interested in reading. And the final section, he covers transitioning to fiber to the home, and how we just continue to evolve and push fiber deeper, and when it makes sense for different operators to go to fiber to the home. So again, phenomenal paper by Dr. Campos. He did present it at SCTE, but he only got 15 minutes to cover a 45 page long paper that had great insights, great coverage. The final slide, if you can pop that up for 1 second, everyone, you can grab, if you want the link, I have a bit.ly link, the full link, and then there's a QR code. If you snap the QR code with your phone, that'll take you to the link if you want to get his entire paper. Greatly thank Dr. Campos and his colleagues who collaborated with him on writing the paper. It's a great paper. I think it's a good industry paper too for people. So Patrick, couldn't help but respond to that particular subject. Dick Beard tells a great story about how life was in the old days, well before good F connector standardization, and how tolerances for every different type were so poor. So thanks, Patrick. That sounds like it'd be an interesting read. I'll have to look into that. Jeremiah D says, at what point do you overload the composite power input for a modem F connector port and its chipset's capability? How high can we push dBMV for that 1.5 gigahertz of D4.0 OFDM? Sounds like a lot for a device. So John, I remember, I think with DOCSIS 3.0, the total power that we could push into the downstream of a modem was like 33 dBMV total power.
Like 30 or 35.
It's around that range. So if you add up all of your SC QAMs, all of your OFDM, like all the channels, not just your DOCSIS channels, but even the video channels, you have to look at all the power that goes into the modem, add them all up, and that total power.
But normally at the house, you're hitting close to zero.
Correct.
So, I mean, the composite power should be really low. We're more worried about the composite power hitting your amplifiers out in the field because that's where it's high.
Yes.
And then you probably put them even higher. So the secondary hybrid inside the amplifier is getting hit even higher. So that's what our worry is. Inside the modem in the house, it should be low. I'll give you an example. If every single carrier QAM, 15 dBMV, 100 channels, 10 times the log of 100 is 20 dB. 20 plus 15 is 35. So you'd have to have 100 channels all at 15 dBMV to hit that 35 mark.
Yes.
Who the heck is doing that? That's a bad design if you're wasting that much energy hitting 15 dBMV at the house for every single channel.
But it does happen. I mean, there are houses where we see plus 20, plus 25 dBMV going into the house, and they're scratching, why can't this modem come online? It's like, well, someone did either put in the wrong tap value, or they were doing some troubleshooting and put in the wrong tap value. And then the modem won't come online because there's too much total composite power going into that modem.
Yeah, I mean, that's like you're throwing money away too.
Yes.
I mean, your design is to try to hit each house with good MER, low enough levels that you still have plenty of level on the plant to go down to the next guy. If you're giving a lot of power to this house, that means you're taking away from somebody else's house.
Yes.
Right? So
exactly. And Grab a Sandwich says, have a good mic, guys. Day. So thank you, Grab a Sandwich. And I think, John, that takes us to the end of the show. Thanks so much in the chat room. That was a great chat. Thanks for tuning in, everyone. We hope you have enjoyed today's dive into the future of HFC network and DOCSIS technologies. Thanks for all the great chat. Be sure to subscribe and hit that notification bell so you don't miss our next episode. And as always, a big thanks to the legendary John Downey for his insightful and expertise. Until next time, everyone, stay curious, stay connected, and we'll see you soon on Get Your Tech On. Take care, everyone.
All right, take care. We'll see you.